Today, we're going to pry open the lid on the devices you use every single day. You know, your laptop, your phone. We're going to demystify the incredible hardware inside that makes them all tick.
I mean, really think about it. The device you're watching this on right now, it feels like magic, doesn't it? But it's not. It's actually this incredible symphony of engineering. And in the next few minutes, we're going to pull back that curtain and show you exactly how it all works.
Okay, let's dive right in. If you want to understand any computer, and I mean any, from your tiny smartwatch to a massive supercomputer, you first have to look at its basic anatomy.
So this diagram here is basically our roadmap. At the heart of every single computer, you've got these three fundamental parts. You have the processor, which is the brain, you've got the memory, which is kind of like its workspace, and they both need a way to talk to the outside world. That happens through input and output devices, or just I/O for short. This constant conversation between these three parts is what makes literally everything happen.
All right, so let's zoom in on the two most critical players in that whole conversation. The part that does all the thinking, and of course, the parts that do all the remembering. The CPU, this is the engine of your computer, plain and simple. When you hear about its speed in something called gigahertz, or GHz, that's literally how many billions of calculations it can perform every single second. It's wild. And modern CPUs have multiple cores, which just means they can think about several different things at once. So the more cores you have and the higher that speed, well, the faster and snappier your computer feels. Okay, this analogy is just perfect for explaining the difference between memory and storage. Think of your RAM as your workbench. It's super fast, and it holds everything you're currently working on. But, and this is the key, when you turn the power off, that workbench gets totally cleared. That's why we call it volatile memory. Now your storage, that's your hard drive or your SSD, that's the filing cabinet. It's a bit slower to access, but it keeps everything saved for the long term, even when there's no power. That makes it non-volatile. See the difference? So that brings up a good question, right? If RAM forgets everything when the power is off, how does a computer even know how to start up in the first place? Well, that's where ROM comes in. It's this tiny little chip with permanent, unchangeable instructions. It's like the computer's muscle memory, and it has one job: tell the computer how to wake up and get going. And how do we get all our information into that brain and memory? Well, we use input devices. Your keyboard and mouse are the obvious ones, of course, but so is this classic Scantron sheet. An optical reader scans your little bubbles, turning those physical marks into digital data the computer can actually understand. It's the bridge between our physical world and the computer's digital one.
Okay, so now we get the core components, right? We know how we talk to them. So let's zoom out a bit. We're going to see how those exact same building blocks, the CPU, the memory, and the I/O, are used to build a whole family of very different computers.
You know, computers really fall into just a few simple classes. You've got the portable stuff in your pocket, the desktops that stay put, and the big multi-user machines. But here's the crucial point. They all use the exact same architecture we just talked about. A server, for instance, is really just a computer with a much beefier processor and way more memory, all designed so that lots of people can use it at the same time.
And then you have the absolute giants, supercomputers. And these aren't just single computers. They are these massive systems with thousands upon thousands of processors all working together all at the same time. They are built to tackle the biggest challenges we face as a species, everything from forecasting climate change to designing new medicines.
Okay, let's keep zooming out. We're going past our own devices, past the supercomputers, all the way to a global scale. Because it's time to uncover where the cloud actually lives.
This is the big aha moment for so many people. The cloud isn't some magical, invisible thing floating around up there. It has a physical address. It's really just someone else's computer. Or, to be more accurate, thousands of someone else's computers.
And those thousands of computers, they live right here, in a data center. These are incredibly secure, climate-controlled buildings absolutely packed with servers. I mean, every photo you upload, every email you send, every movie you stream, it's all stored on physical hardware, sitting on a server rack inside one of these buildings somewhere in the world.
And we can take that idea of massive computing even one step further. What if you could connect computers from all over the world to work on one single problem? Well, that's grid computing. It's like the ultimate form of digital teamwork. A central server breaks a gigantic problem down into these tiny little pieces and then sends them out for thousands of computers to help solve. It's an amazing way to pool our collective power for things like medical research or searching for extraterrestrial life.
So we've seen the basic parts, we've seen how they scale up, and we now know where all of our data actually lives.
The final question is, where is all this incredible technology headed next?
You know, one of the most important trends right now is green computing. Think about it. All those data centers and the billions of devices we all use, they consume a tremendous amount of energy. So the goal here is to make every single part of a computer's life, from manufacturing it with recycled materials to designing data centers that use way less power for cooling, as sustainable as possible.
And then there's the next great leap, something that sounds like it's straight out of science fiction: quantum computing. These machines, they don't think in ones and zeros like everything we've talked about. They use the truly mind-bending rules of quantum physics, which allows them to explore millions of possibilities all at once. They have the potential to solve problems in medicine, in material science, that are just simply impossible for even the fastest supercomputers we have today.
You know, from simple machines that just counted numbers to planet-spanning networks to these emerging quantum machines, the journey of computer hardware has been absolutely incredible. And that really just leaves us with one final thought. What problems are we going to be able to solve when the next generation of hardware finally arrives?